In the previous video, we introduced the s orbitals, which are the simplest orbitals you can get in the hydrogen atom simply because the angular parts are constant. In this video, we're going to start talking about the orbitals for L greater than 0. So the first such orbitals are the p orbitals, for which L is equal to 1. Now in the last chapter, we introduced the p orbitals, and one of the things we noticed was that for L equals 1 and m sub L equals plus or minus 1, the orbitals are complex, or the spherical harmonics are complex, which makes it more difficult to see what's going on with them and to interpret them. And so traditionally what we do when we come across things like this is we switch to what are known as the real spherical harmonics. And so we can define linear combinations of these spherical harmonics here, the y, l, ml, to give real orbitals, and that's what we're going to start with. Okay, so to start, let's look at a linear combination. So this 1 over root 2 is there for normalization, and you add up y1 minus 1 and minus y1 1. So this minus sign is just because there's some strange conventions in here, and this is the way it will work out. So if you plug in these definitions, you will get this. And if we use the definitions we get from spherical coordinates, we can see that this should be equal to x divided by r. And we call this the px orbital. Now if we take a different linear combination, we see that this becomes 3 over 4 pi square root sine theta sine phi. And using the same argument from above, we know that this has the Cartesian representation y over r, and therefore we write this as py. And then the last one is pretty straightforward. So y1, 0, so L equals 1, m sub L equals 0. This is straightforwardly just 3 over 4 pi cosine theta. And for all the same reasons, we can rewrite this as z over r, and we call this the pz orbital. Okay, so now this defines 3 different angular functions. One is aligned either along the x, the y, or the z axis. And this, if you look at 3D polar plots of this data, this is similar to plots we saw in the last chapter. What we're doing is we're drawing a distance away from the origin that corresponds to the particular combination of theta and phi. And now we're color coding based on the sign. And so we see that the px orbital has this positive lobe in the positive x direction and a negative lobe in the negative x direction. Y similarly has a positive lobe in the plus y and a negative lobe in the minus y, and z has a positive lobe in the plus z and a negative lobe in the minus z. Okay, so these are your 3 p orbitals. These are the real orbitals. So these are the real p orbitals. And note, however, that because we have linear combinations of these spherical harmonics with different m sub L values, that px and py are no longer eigenfunctions of Lz. Okay, so whereas Lz applied to pz will give you h bar times 0 equal to 0, if you apply Lz to px, this is equivalent to applying Lz to 1 over root 2 y1 minus 1 minus y1 1. And if we expand this out, what we'll see is this is h bar over root 2. We apply Lz to y1 minus 1, and we should get minus h bar. So this is minus y1 minus 1. And now this is, you apply Lz to y1 with n sub L equals to plus 1, you'll get plus h bar, so this remains minus So this is equal to minus h bar times 1 over root 2 y1 minus 1 plus y1 1. And now this term here is not the same thing as up here. And so this tells you that px and py are no longer eigenfunctions of LZ. These plots are really instructive for understanding what the p-orbitals look like, but it's actually missing a whole lot of information because this is only the angular part. And remember, we have these radial parts. And so to understand the complete solutions, we should look at the radial part and the angular part together. And we're going to do that not in the next video, but in the video after. So first, in the next video, we're going to introduce the d orbitals, which have similar structure, and we can do a similar analysis. And then after that, we'll look at different ways to visualize these complex three-dimensional orbitals all together. So we'll look at the s, p, and d three-dimensional functions all together after we introduce the d orbitals in the next video.